Hello friends, welcome to the tutorial on regular expressions and finite automata. In this tutorial, we are going to understand the relationship between regular expression and finite automata, and we'll learn to construct non-deterministic finite automata from the given regular expression. Regular expressions are the patterns used to define strings or languages. They are constructed analogously to the arithmetic expressions by using set of operators. The relationship between Fa and regular expression can be visualized like this. If we have a regular expression available with us, there exists an equivalent Nfa with epsilon move to it. Similarly, if we have Nfa with epsilon moves available, its equivalent Nfa without epsilon moves can be constructed. If we have Nfa without epsilon moves available with us, its equivalent Dfa can be constructed. Similarly, if we have a Dfa, that is deterministic finite automata, we can construct an equivalent regular expression to it. It's the definition of regular expression. If we have alphabet available with us, say summation, then any terminal symbol available from the alphabet can also be referred as a regular expression if it is available individually. Like here, A, B, these are the terminal symbols available. Then A or B or any other symbol from the alphabet is referred as a regular expression. Similarly, epsilon and phi are also referred as regular expressions. The union of two regular expressions is also a regular expression. Say for example, we have regular expression A and a regular expression B. Then its union is also a regular expression which can be represented as A plus B. Stands for either A or B will be available in the resultant string or language. Concatenation of two regular expressions is also a regular expression. If we have two regular expressions A and B, in that case A followed by B or B followed by A can be represented as A dot B or B dot A, where dot is acting as a concatenation operator. Interaction or the closure of regular expression is also a regular expression. For example, if we have clean closure of A, in that case A star, which is nothing but clean of A, is also a regular expression, which means 0 or more number of times repetition of A. Similarly, if we have A plus, in that case positive closure of A means 1 or more number of times repetition of A is also referred as a regular expression. If R is a regular expression, in that case R enclosed within round bracket is also a regular expression. All the expressions over alphabet precisely defined recursively by the application of rule 1 through rule 5 are regular expressions. That means if we are using either one or multiple statements available from here and we are using them recursively, then the resultant expression is also referred as a regular expression. Let's see the different examples for regular expression. Here we are using alphabet equals to containing two terminal symbol A and B. So in that case, epsilon will also be a regular expression representing 0 length string from the given alphabet. A, B, A plus, that is positive closure of A, clean closure of A dot B, that is A followed by B, A plus B, that is A or B, that is either A or B, A plus B whole positive closure, which means either A or B or both will be repeated for 1 or more number of times. A plus B whole star, which means either A or B or both will be repeated for 0 or more number of times. A followed by A or B star, which means A followed by 0 or more number of times repetition of either A or B or both. In other words, this can be expressed as any strings over a given alphabet starting with A. Here we are talking about any string or an alphabet A, comma B starting with B. Here all the strings or an alphabet A, comma B ending with A. Similarly, all strings ending with A or all strings containing A or B ending with B. Here we are talking about small a as a substring for A or B. That is the string from the alphabet summation containing two terminal symbol A, B all the strings which will have small a as a substring are expressed with the help of this regular expression. Let's see how to construct Nfa with epsilon mu from the given regular expression. By Klein's theorem, if epsilon is a regular expression, then its equivalent Nfa with epsilon mu can be constructed like this. Here we have connected initial state with that of final state with the help of epsilon. That means on no given input, that means when we have zero length string as an input, that is epsilon, the final state can be reachable from initial state. If A is a regular expression, then its equivalent Nfa with epsilon mu can be constructed like this. One can see here that this A is connected from initial state with the help of epsilon, and from this state on the input of epsilon the machine can move to final state. Similarly, if A dot B or A plus B, that is concatenation of AB or of AB is available, that is union of AB is available as a regular expression, its equivalent Nfa with epsilon mu can be constructed like this. This is for concatenation of AB. That means in order to reach to final state from the initial state, we require A followed by B. And for A or B, it can be Nfa with epsilon mu can be represented like this. Here one can very easily understand that from initial state, in order to reach to final state, we need to traverse the path. Machine need to traverse the path either through this or through this. That means either A or B will be the part of resultant string, or the string which is accepted by this Nfa. Let's see how to construct Nfa with epsilon mu equivalent to the clean closure and positive closure if A is a regular expression. Here is the example for clean closure of A. Here we are assuming that the regular expression, the Nfa with epsilon mu from the regular expression A is represented like this. Here, in order to reach to final state, if we are traversing this path, it means A exists for once. If we want to represent epsilon, that is 0 times repetition of A, in that case from initial state the machine will traverse this path in order to reach to final state. Whereas for the occurrences wherein A is occurring for more than one number of times, the path to be followed will be A. Then with the help of this epsilon we move back to this state, again another A, third occurrence of A, fourth occurrence of A, and so on. And at the end we will reach to final state through this path. Similarly, for A plus, which means one or more number of times repetition of A, we need to remove just this transition from the Nfa with epsilon mu. The resultant Nfa with epsilon mu is this, that is for single movement this path will be followed, whereas for multiple occurrences of A, this state will be traversed. From this state we will traverse to this state again in order to repeat A. Let's construct a Nfa with epsilon mu equivalent to the given regular expression. Like here we are having A followed by A or B whole star followed by B. If we observe this, we can find out that this expression is a combination of three different sub-expressions. Like here, this A can be constructed as one sub-expression. This whole clean closure can be considered as another regular expression, and this B itself is a third regular expression. So we have three sub-regular expressions available here. We'll construct Nfa with epsilon mu one by one by using these sub-regular expressions, and then we'll combine these three in order to get the final Nfa with epsilon mu. So this is for first A, that is this. For A plus B can be constructed like this, either A or B. Then for epsilon, that is this state is connected to this state which bypass this entire A or B path, and this is for multiple repetition of either A or B or both one by one. And last but not least, for this B, the NFA with epsilon mu can be constructed like this. So here we have A followed by this entire thing for A or B whole star and followed by this B, which concatenates one sub expression with the second followed by third. We'll see how to construct a NFA without epsilon mu from the given NFA with epsilon mu here. We need to use this expression for the same. First of all, we require to calculate epsilon closure for all the states available in the given NFA with epsilon mu. An epsilon closure is nothing but the collection of all the states which are reachable with the help of epsilon from any given state. So in order to find NFA without epsilon mu from the given NFA with epsilon mu, we will use this. Here delta dash represents the transition function for NFA without epsilon mu, whereas delta represents the transition function for NFA with epsilon mu. Here first we calculated epsilon closure for the state for which we are seeking transition for delta dash. Then from all these epsilon closures of Qi, we'll find what is the transition on Xi input. Then for all the set of states, we'll find out epsilon closure. The resultant is nothing but the combination of states where machine can move on the input of Xi from the given state Qi. We'll take the same example which we have seen in the previous slide, and for that we'll calculate delta dash from the first state on the input of A. So here we need to first calculate epsilon closure of 1, which is nothing but 1, 2. That is from 1 itself is epsilon reachable. Similarly, on the epsilon from 1 we can reach to 2. So 1, 2 comes under epsilon closure of 1. Followed by, then we have taken on these individual state, from this individual state on the input of 1 where transition can move. So for example here delta of 1 comma A, if we see this on the input of A we are not having any transition as such, so this will result in 5. Similarly from 2 on the input of A we are reaching to 3. So result is 3, that is 5 union 3 equals to 3. We will need to find the epsilon closure of 3 now. Here epsilon closure of 3, what does it mean? That 3 itself, 4, 5, 6 and 7. Sorry, 6 and 10. 7 is reachable from here, like epsilon followed by epsilon. So in all, epsilon closure of 3 is having different states such as 3, 4, 5, 7 and 10. So delta dash of 1 comma A, that is the equivalent move for the NFA without epsilon move for 1 comma A is from 1 on the input of A, machine can go to 3, 4, 5, 7 and 10 states. The conversion of this diagram, that is NFA with epsilon mu to NFA without epsilon mu, is shown here. This is the given and this is required. We have seen that from 1 on the input of A we had these moves. So let's see here what we are getting. From 1 we are having epsilon closure as a 1 and 2. So we have combined these two. On the input of A we are reaching to 3. So from 1 comma 2 on the input of A we are reaching to 3. From 3 we are having epsilon closures as a 4, 5, 6, 10 and this. So if we take A as an input, this can be represented like this: 1, then this A. From this 6 we can again reach back to 4, which means again 3 and 4. So on A we can now clean to the same state. Similar explanation can be given for B as well. So from this state on the input of A and B we have cleaned. Similarly on the input of B, from here either we can go to this, or with the help of this B we can reach to a state 11 whose epsilon closure is 11 and 12 both. Now here we can see that 11 in the earlier diagram, that is given diagram, is a non-final state, whereas 12 is final. Here we have shown 11 and 12 both as a final, because from 11 on the input of epsilon we are reaching to final state. So every state which is having final state as a epsilon closure to it, we can show as a final state. So thank you. If you are having any doubts, kindly comment.